Hello, Lane Bloom here to walk you through the first remark on page 190 of Dummett and Foote about the hierarchy of group attributes. I've included all the definitions of the relevant terms and some theorems that are super important later. Feel free to pause on those if you would like at some point to come back to those. And same with the proofs. I gave more complete proofs, but I'm going to walk you through the real heart of the matter of these as we go through. So that every cyclic group is abelian boils down to the fact that in a cyclic group, you can think of the group operation as reducing down to addition on the integer exponents of a generator, and of course, addition of integers is commutative. That every abelian group is nilpotent is also fairly fast. It comes pretty directly from the fact when you are constructing the upper central series, the first term is going to be the identity trivial subgroup, and then you get directly to the center, which in an abelian group is the whole group. So if you have a non-trivial abelian group, you have a nilpotent group of class 1. And if you have, though, the trivial abelian group, you have a nilpotent group of nilpotents class 0. Okay, every nilpotent group is solvable. This one requires going back up to those definitions of the lower central series and the derived series, and then theorems 8 and 9, which show conditions for groups to be nilpotent and solvable, respectively. And the real work of this proof is on a remark that Dummett and Foote made that is one line or a couple lines there, but the proof is not necessarily immediate. And I go ahead and prove that here, that this G upper with parentheses I is always a subgroup of G upper, just regular I. And then once you use theorems 8 and 9, you get that if you have a nilpotent group, then you can make this lower central series, which terminates in the identity group. But then by the lemma, if you try to make a derived series, well, then you're going to get the G upper parentheses in also has to be the identity because it has to be contained in G in from the lemma, which is the identity. So you can kind of just, because every single one of these G I's is contained in the other G I's, parentheses to not, it follows almost immediately from that. Okay, that every solvable group is a group. Definition. Okay, not every abelian group is cyclic. Klein 4 group's a counterexample. It's abelian, it's abelian, but every non-identity element generates a subgroup of order 2. That's a proper subgroup, not the whole group. That not every nilpotent group is abelian. D8's a counterexample. You can start building up those quotient sub centers. First, you get the trivial subgroup of D8, then you get the center, which is just identity in R squared. When you create D8 mod its center, which is isomorphic, we know, to the inner automorphisms of D8, what you end up getting is the Klein 4 group, which is abelian. So it has order 4, the whole group, Klein 4 group. So when you look at the argument based on the orders of these different groups, you end up getting that the Z2 that you get has to be the whole group. So that sequence is going to terminate, hence D8 is nilpotent, but of course it's not abelian. For example, S and R don't commute. Okay, not every solvable, yeah. Not every solvable group is nilpotent, yeah. And S3 is a counterexample to this. Of course, A3 is an index 2 subgroup, so it's normal. So this is going to end up being a composition series for S3. S3 mod A3 is Z2, which is abelian, and A3 mod just the trivial group is going to be isomorphic to A3, which is isomorphic to Z3, which is abelian. So that is a composition series for S3, hence it is solvable. And finally, not every group is solvable. So here, A5 is a counterexample. We know that A5 is a simple group, so its only normal subgroups are the trivial group and itself. So the only potential composition series would be this little bitty one here. But when you take the quotient of those two, you get A5, which is not abelian. So A5 is not solvable. Hope that clears this up and connects the concept really well.